Showtime for our RNet project. First, the dataset we work on is called SQuAD. It provides high-quality dataset in large scale for reading comprehension style question answering task. This task is like given a passage P and a question Q. You need to predict an answer A based on information found in the passage P. In SQuAD, the answer is constrained to a continuous segment of the passage, so it can be long phrase and contains non-entity words, as shown in the example on the right. Thus, it challenges us to really understand the semantic meaning of both of the question and the passage. There are several models work on the SQuAD dataset, and neural network-based models are most effective ones. From the table on the right, we can see that the RNet model has the best performance for both of the single and ensemble models. It inspires from the MatchLSTM model. There are two major contributions of this model. First, it adds a gate to the attention-based recurrent network to account for the fact that words in the passage have different importance to answer a question. Second, they introduce a self-matching mechanism to dynamically aggregate information from the whole passage to predict the answer. Then my partner will introduce the RNet structure.
So the basic structure of an RNet consists of 4 layers. The first one is a question passage encoding, and then the next one is a passage matching layer, which generates a representation with question awareness, and then is a layer that's doing passage self-matching, and then we have an answer prediction layer that generates the output to predict the start and end of an answer. So the first layer of the RNet is called question and passage encoder, and what it does is basically convert words in the passage and question to its corresponding word embedding and feed them through a bidirectional RNN to get what they call the character level embedding for each and every word, and sort of use them as the representation of a word, and then run them through another bidirectional RNN to get a representation of passage and question. Basically, the whole purpose of this layer is to encode the question and passage to a format that the latter layers could process on. And also, it uses GRU instead of LSTM because they sort of achieves the same results. And the next layer is called the gated attention-based recurrent network, which is, I think, the essence of this paper. And what it does is basically produce a passage representation with question awareness, because normally when you do question answering, the passage is sort of independent from the question. And in this paper, this is sort of the novelty of this idea. And basically, it's just an RNN from the output of the passage representation, and except we are using an attention which is calculated from the question representation, and we're not using word by word, but we're using the whole question as an input to calculate the attention, and we are using some softmax and sigmoid, and then feed them to a GRU cell. The next layer is going to be self-matching attention network, which sort of adds the passage context to the word representation from the previous results, because as we remember, the previous layer doesn't really have the notion of a context. It only has the awareness of question and the word themselves. So similar to the previous network, this one uses a bidirectional RNN, and the cell looks like this, where they use attention again calculated instead from the question. They're using the passage representation to calculate the attention and feed them through almost the same sort of structured bidirectional RNN, and produces the hidden states as the results. And the output layer is basically a pointer network to predict the start and end position of the answer. And the idea is to use attention to select the start position and end position. And you can see from equations right here, where we're using the hidden states and the results from the previous layer as sort of the input, and we're doing tension tricks, do a tangent edge, and do softmax. And the AT here is some potential predictions, and we're using an argmax to select the best answer. And one thing to remember is that there's only P1 and P2, which means there's only 2 occurrences of this network cell, and which also means that initial value of this hidden states is very important and is thus determined by these 3 equations right here, and it's basically another sort of softmax on top of some weight-based attention, and this is the whole structure of RNet.
So in terms of implementation details, we find that thinking in shapes always helpful because it's sometimes kind of hard for us to understand the objects in higher dimensions, but the shape of tensors can help us get intuition of how these objects are put together. And following the same convention throughout the whole implementation is also very necessary. For instance, the inputs to the RNN networks can have different kinds of shapes, but throughout the whole implementation, it's better just to stick to one convention. And turn to the next page, we talk about the challenges of reproductivity that we were faced with. So the first thing is the inexplicit statements such as weight sharing, or whether they used bidirectional RNN or unidirectional RNN. And we all had to guess for ourselves. And the paper were also not very clear of how they handled variable length sequence, or how they did dropout or normalization. So these are all challenges.
This table shows exact match and F1 scores of several algorithms and implementations we started. As an observation, even though RNet remains the best model on SQuAD leaderboard, it seems pretty challenging to reproduce their work. Existing open-source implementations are not comparable to the performance that Microsoft Research has achieved. In our work, we tried to implement RNet architecture in TensorFlow. We have devoted a large amount of time and effort studying different versions of RNet implementations, training, and testing. However, due to the ambiguity in the paper and the many technical challenges previously mentioned, our work cannot reach the expected performance. Probably we misunderstood several important details or have bugs in the code. Furthermore, we propose these areas for future improvement. First, using Theano backend, which is faster than TensorFlow. Second, integrating syntax and knowledge base information into our system. Last, designing an architecture to handle questions that require complex inferences. So that concludes our presentation. Thank you.